before.
Yeah, that's the
Maybe
thing.
I didn't solve the next one. Can we see it?
So this actually wasn't on the contest. It was like it was like on the short list for the contest. Okay, so we want to draw the AX center. So I'm going to do this. All right, so we have encircle omega. There was a problem with the Feurbach point too. Did you solve that one?
I tried it, but I couldn't.
All right.
I didn't read the solution because it was too long.
So we could always do that if we run out of time too. All right, so I'm going to draw the encircle. Let's draw the X center.
You can draw X center more easily than just adding those points. Like you can take the angle bisector tool.
Yeah.
And like click on lines. And that will draw both bisectors between those two lines.
You mean kind of use the in center, X center lemma?
No. No, you take the angle bisector tool in the GeoGebra. And then you click on not the points, but rather on lines.
Oh. Oh, you can click on the lines and it draws both.
Yes.
That's cool. I did not realize that.
I just saw that you always construct
those points,
adding those 2 points, and it just bothered me.
Yeah, it's all good. All right. Okay, we can delete this and this. So DEF is the in-touch triangle. And P is the intersection of EF and BC. So we know that's basically in harmonic conjugation with BD and C. Oops. This is P. Okay, so we draw the circle with diameter IAP. Okay, so we want to show basically if we let AD intersect EF, right, does that look right? Yeah, if we let AD intersect EF, we want to show that that point has the same power with respect to the incircle. I'll call it something else, K. We want to show that K has the same power with respect to the incircle and that circle.
That circle looks like it passes through the midpoint of EF.
Okay.
IAP, that circle.
All right. Interesting. All right, let me rename the midpoint of EF.
Well, it's obvious because IA bisects EF, and they are perpendicular.
Oh yeah. So basically, since this is a right angle right here, then this has to be a right angle, and so yeah, that's proves it. Okay. Let me hide some of this extra stuff.
Yeah, we are done by well-known projective lemma. KH times KP equals to KE times KF, because PKEF is an harmonic bundle and H is the midpoint of EF.
Oh. Oh yeah, that's like too easy. Okay, so that proves part A, right? And then let's see, is part B just as simple? We want to show that that common chord bisects BC. Or the common chord of that and the this circumcircle.
Can you name
Okay.
the midpoint of BC?
Yeah. So yeah, part A was pretty easy. Part B.
Okay, this is also obvious because LD times LP equals to LB squared and LD equals to LJ, so we are done.
Okay.
Actually, we don't need the right
Harmonic bundle again.
Yeah. Just harmonic bundle twice in a row. Yeah. So, okay, let H be the midpoint of EF. And let let J be the so yeah, do we even need point J? Wait, we want to show IAP.
Yeah, we need the point J.
Okay, be the perpendicular from IA to BC. Oh yeah, we do need it. Yeah. So IAJP equals 90. That means J lies on the circle with diameter IAP. Also, angle IAHF equals 90, or angle IAHF equals angle IAHP equals 90. That means that IAJHP is cyclic. Also, B, C, D, and P are in harmonic conjugation. That's well known. Using pole and polar. Or actually, that's just the Dragone point. Yeah. So that means that F, E, K, P is harmonic. And that means that HK, KH times KP. Anything about this? KH times KP is equal to KF times KE. It's KP. I didn't even define K, so I'll do that. IP, say, common chord of, let me just cheat. Oh, whoops, KH times KP equals KF times KE. So let EF meet AB at K. Okay. So I'll say that these three concur at K. K. Okay. And then the same thing is true. A similar argument is true with L. So let L be the midpoint of BC. Then we have B, D, C, P are in harmonic conjugation. Which means that L, what is it? LB times LC equals LJ times LP. Is that right?
It's actually LD times LP, but LD equals to LJ, so we are done.
Okay, so that's, yeah, LD times LP. But it's still LB times LC in the certain circle of ABC, right? Oh, it's LD times LP is LB squared. Yeah, okay. Then, so this is LJ times LP. So then that shows that these yeah, I'll just write out the conclusion. All right. So we can go back to the problem from I-3435. By the way, I was going to ask you guys, what do you think about shortening the sessions from 3 hours to 2 hours? Would you guys, how many of you would be in favor of that? And how many of you would like to keep it at 3 hours?
You cannot do anything in 2 hours, I think.
2 hours is too short.
Yeah.
Okay. All right, I'll keep it at 3 hours.
I think 3 hours is better.
Okay. All right, sounds good. So I'll keep it at 3 hours. We could go, so Serdar, you said you already did this problem. Do you want to go back to this problem? No, I'm sorry. Which was it? Oh, this one. Or we could look for a new problem.
With the Feurbach one, actually, we can do it. I don't know the solution because.
Okay. All right. So I will copy that into a new window. All right. I'll just say same contest. I know it had a long name. Put this up in 2 lines. All right. So FE is the Feurbach point. Let's draw the 9-point circle. And then let I be the center of it. So you have D, E, and F. And then let's draw the 9-point circle. Whoops. Didn't want to do that. So here's the Feurbach point. Let me try to make it closer to A, just because I think it looks nicer. So I'll call it FE. Let's see. That looks kind of nice, I feel like. So then we have DI intersect AFE. Here I could just draw it as a segment. So that's P, and then we have BC intersect EF, which is like the same point as last problem. So this is Q, and we want to show the radical axis of IDQ, and IPEF is the I median. This is kind of interesting. So let's draw the, so we know G is the midpoint of BC. We're going to draw those 2 circles. IDQ and IPFE. And this obviously passes through. Okay, never mind. Well, this will pass through the midpoint of EF, like we said in the last problem, right? Yeah. And so maybe I could draw a line AKI for just a segment at least. There we go, something like that. So we have that circle and then IPFE. And we want to show that G. So basically, I guess another way to say it is that GI and that point are collinear. Or we could just say G has the same power with respect to them. That's kind of a nice problem. Okay.
DFE, HJ, and EF concur.
HJ and EF.
And DFE.
Okay. DFE.
Have you used that fact some in a problem before?
Wait.
DFE.
So DFE is this circle, right?
Not the circle. Just the line DFE, line DFE.
Line DFE.
D Feurbach point.
Oh, whoops. My bad. Interesting.
But I don't know how to prove that. I just saw that as a problem somewhere.
We proved that in an earlier session to solve a problem about Feurbach point.
Oh, okay.
All right. So that is a tricky diagram. What if I make it more? Yeah, I think it was okay before, I guess.
You can redefine the points because they disappear because you segment. You draw the segments.
Yeah, because like, yeah, this only works if P is on the segment ID.
Otherwise, it's better, I guess. It looks.
Oh, do you think it looks better when P is off the segment ID?
Yeah.
Okay. So I'll make this a lot, or yeah. Let me let's see if this makes the circle go away. Yeah, let me make this like the line ID. There we go. Now we should be okay. So this point will be P. And that should help fix some stuff. Okay, we have Hakan joining.
FEDG is the Euler, the 9-point circle of BIC.
Okay, hold on just a
This
second.
is by Poncelet point.
Okay. So FED.
FEDG, Feurbach Point and points D and G.
Okay. That's the 9-point circle of what?
BIC.
Oh, interesting. You use some stuff about the Poncelet point?
That follows from the Poncelet point, I think.
Okay. All right, so IDQ is this circle. Oh, I forgot to draw IPFE. Is that circle. All right. Okay, so this circle is the 9-point circle of BIC. Okay, so we want to show G has the same power with respect to those two circles. So we know that GD times GQ is GB squared, right? So we can calculate that. We just want to see what's the power of G with respect to IPFE. Okay, so K, there's actually, yeah, there's that point of concurrence that you guys mentioned. I'm not sure if it's useful for this problem or not, but it could be.
Maybe we should invert, since the power of G with respect to IDQ, that is equal to GB times GC, which is just GB squared. So we need to prove that circle with diameter BC is orthogonal to the IPFE.
IPFE, yeah. Interesting. Okay, so maybe inversion might help. So
maybe we should invert about circle with diameter BC.
Okay. Yeah, it almost looks like there's some just these concur. It looks like
that is the iron lemma.
That's the Iran lemma.
Yes.
Okay. I always thought the Iran lemma was like, okay. So this is saying the foot of the altitude from B. Oh no, I think the fact that these concur is just the fact that the 9-point circle passes through the foot of the altitude, right? That's why these concur, right? These three? Yeah. Okay. Yeah, sorry, I keep moving this a bunch of times. I apologize. But yeah, that probably looks pretty good. Yeah, I don't want this circle to look like it passed through B. Okay. All right, so Khan is on, Stefan is on. Got a little, almost an hour left, just a little less than that. Okay, so we want to see what happens when we invert about this circle, right?
I just want to say that concurrency of H, J, EF, and DFE, I think it is not hard to prove, just in case we would need that later.
Okay. Yeah, that's what Serdar was saying we proved on a previous session, right? But I guess if we want to prove it again, it's not hard.
I think it is just the power of a point.
Okay. So do you want to go over that proof again? Or so you think it's just power of a point? Sorry.
Yeah, I think it is just the power of a point. Of course, using the fact that the Feurbach point exists, like there is an intersection.
So once you know the Feuerbach point exists, how do you use power of a point to show that?
Maybe we can first use like phantom point, so intersect H, J, D, E, F, and that point.
Yeah, sorry, it's
a bit small. And then we define FE as the intersection of DM in circle.
Okay.
And then we do a powerful point to prove that FE lies on the 9-point circle.
Okay.
And that proves that. So MF times ME, that is equal to MD times MFE.
FM times ME is FE, is FEM times MD.
And that is equal to MJ times MH, I think.
How do we know that? Oh, well, I guess we just need to show FM times FE. FM times ME is JM times MH, which is kind of like the same as showing that that's cyclic, right?
I think so, but that doesn't look right. Maybe I made a mistake, I don't know.
Sorry. Let's see. So, oh, we want to show that GJ FEH is cyclic. Yeah, not D. So,
oh yeah, that is not obvious at all. So,
okay. All right. So yeah, do you think inversion? Oh, I guess the fact that these concur is Iran lemma. Maybe that's but do those concur? Let's see. These three circles. So EF, the perpendicular, or EF, CI, and what's the last circle? So EF, oh, I just drew this. Yeah, never mind. This is the find and pass through M. But
inversion of FE lies on EF.
oh, it looks like
Feurbach point.
CI and M are linear. Okay, inversion of EF lies on what?
The Feurbach point inversion of that point lies on EF.
Okay.
I'm not sure exactly why.
Oh, and it looks like it's the intersection of EF with that circle.
It is because we should prove that those are orthogonal, so the inversion would lie on that circle. Since that circle inverts to itself.
All right. The image of the whole line EF. Let's see. Oh, it looks like it is the circle FMG. Or FE, sorry, FE, Feurbach MG.
It is the 9-point circle of BIC. Of EF, yes. And also I see that because of the Iran lemma, Feurbach point inverts to a point on line EF.
Okay, from the Iran lemma?
Yeah.
All right.
Probably the same reasoning would apply to why the EF line inverts to the 9-point circle because of the Iran lemma.
Okay. So does this circle invert to itself?
Yes, we should prove that.
Okay. Is it obvious that GFE? Well, oh, that I don't think that's perpendicular. Okay, so yeah, it's like we're trying to invert. There's so many circles here, it's confusing me. But it feels like we're close. So yeah, if we try to invert, if we reflect this about this, it stays the same. If we reflect this about this, it stays the same. Wait, if both of these circles are fixed under inversion, this one and this one, then that means it has to swap I and L, right? So that means that G, I, and L have to be collinear, right?
Yes, if we know that it inverts to itself for both circles,
Okay.
which is the thing we want to prove.
So okay. So yeah, sorry, I'm not as fast as you guys. So this one we know inverts to itself, right? Because we know, but GD times GQ is GB squared, right? So we know D and Q get swapped, and because angle IDQ is 90, does that prove it? Let's see.
I think it is enough that D and Q are swapped.
Okay. Yeah, it's enough that D and Q are swapped. So this circle gets fixed. This circle we want to prove also gets fixed. And it's enough to show that NE and F get swapped, right? Or well, or FE and N get swapped.
I think it is enough.
Okay. And then did you say that like that's like you think that the inverse of FE lies on EF by the Iran lemma?
Yeah.
Okay. So we just have to show that it still lies on a circle. Yeah. Well, wait, then it would So basically, if we hide this circle, we want to show that IFE PN. We want to show that this is cyclic, right? IFE PN.
Yeah, if we define N as the version of FE.
Yeah. Okay. Oh, but then how would we define P? So P is DI intersect, yeah, AFE. That's a good question. The image of the 9-point circle. I think that's, yeah, the 9-point circle. It's a line through N. It's kind of interesting. So you have a couple more like concurrencies here.
Those are the feet of altitudes from B and C of the triangle ABC and that line.
Okay.
And it kind of makes sense that N lies on that line since FE lies on the 9-point circle.
Yeah, that makes sense. I wonder what P inverts to. Yeah, we don't really have anything special for that. So L and I, we want to prove they get swapped. Kind of define FE and N to get swapped. Yeah, we need to understand the point P. All right. So yeah, how do we deal with the point P? Yeah, if you want, we could work on this for like 10 more minutes, and then we could try to go back to that other problem that could be solved like algebraically. We could try to see if we could do it algebraically. Yeah, my brain is getting tired with this one. But if you guys are making progress, I don't want to stop. What do we do with point P?
If you take the perpendicular to EF through N,
Okay.
then that line is in this case, the exterior angle bisector of P and G.
P and G?
Yeah.
let me,
if P is on the bottom, it looks simpler, I think.
okay, I'm a little confused. So this line right here, so it's through N and perpendicular to EF, you said?
Yeah. Oh, that will just mean that EF is the bisector, in this case, the internal bisector of P and G.
Interesting.
And also, I angle traced a bit, so we would need to prove that FE, the angle FE, I'll let you just draw it a bit. I'm going a little bit fast. So the angle FE DI, so that little angle,
Yeah,
in
that
this
thin angle.
picture, that would need to be a half of the angle PNG, but in this case, since P is above the line EF, so it's like if you use directed angles, then I mean, have how
how would it be easier if P lied on IB?
I think my picture is like that, and I think it is a bit simpler.
Okay. All right. Let me draw it like that. Let's see. Let me make this like a very narrow triangle, kind of like this. And then
Maybe you should just delete some circles.
yeah.
There's too many. I don't think most of them are important. Like I don't think the 9-point circle of ABC does much in the diagram here.
Okay.
It defines the Feurbach point, but
There's too much already. Yeah.
yeah.
Yeah, I'm gonna delete this line. This line. Whoa, that scared me. Okay, this is just AN. Wait, what? Oh, this was the perpendicular. Yeah, we were talking about that before. So that was to say that EF bisects angle ANP, I think, right?
Yeah, EF bisects. It is in this case the external angle bisector of P and G.
DNG. Okay. Okay, so EF is the external bisector of BNG. And then what was the other thing you were saying about point P?
In this case, the angle FEDP. FEDP.
Okay.
Angle. It should be half of the angle PNG.
Okay. So
if that were the case, that was just the angle trace. If that were the case, it would be cyclic, and we would solve the problem.
okay.
So that's why the angle bisector of this angle looks important.
All right. Interesting. Okay, so we want to look at angle DNG. And basically we want to show FEDP is half that. So FEDP, we can kind of like if we draw where this meets the end circle, so like the topmost point, yeah, let me hide the 9-point circle. So FEDP that's FEDR, which is half of FIR. So we want to show FEIR. Forgot what angle it was.
DNG.
DNG, that's right. FEIR is DNG.
Not D, but P.
PNG. Okay. Interesting. Okay. So EF is the external bisector of PNG, is what you're saying, right?
Yeah. I mean, I don't know why, but it looks like that.
It looks true. Oh, it says PKG. Wow, this is a tricky diagram.
Oh, I think I know why it is the angle bisector.
Okay.
So basically, we have by the inversion, we would have that QDN FE is cyclic.
Okay. Or QD
And FE.
QDN and FE is cyclic.
It is a really close circle to that, but it isn't the same.
Okay. Okay. QD. Wow, there's so many circles. Oh, that one.
Yeah, that one. And then we would have that angle QDN D FE
Mhm.
that is equal to QNFE,
Okay.
and that is equal to GNE.
Mhm.
I mean, I think this is close. Maybe it isn't exactly the proof, but I mean,
So yeah, so we want to show GNE. We want to show GNE equals PNQ. But wait. Oh, Geo King says GND equals FEQD, which is FEIR. Ah, okay. So I think maybe maybe we've solved it because we showed those two angles are equal. But wait, where did P come into play? Wait, FEIR is G and D. I think we wanted to show that P, yeah, I'm not. I feel like it all that looks better, in my opinion. FEQDI. But FEQDN is cyclic, right? We're pretty, feels like we're close here. Mostly you guys doing the work, but yeah. That'd be awesome if we end up solving this. I could write out the steps we've done so far. Oops. Oh, point C like vanished. So yeah, we know this circle gets fixed under the inversion. We want to show this circle gets fixed also. We could define, so you think you know that FE inverts to something on EF.
Yeah.
We have FEQD is similar to FEIR. That doesn't look true. FEIR is like isosceles, right? Oh, FEQD also might be isosceles. Interesting. Is that really true?
No, that isn't true. It is that P and Q would equal to the single. It is just very confusing with so much stuff on the diagram.
Yeah.
I also got confused by the same thing, so I know.
Okay. So we wanted to show that PNF equals GNE. Let's see. P and it keeps clicking K. FNP and ENG. Yeah, FNP equals ENG, basically, is what we want to show. But FNP is QNP. This is where I think we use that circle. FNP, never mind. So FKP wait. Wait, how does this work? What does that circle? Okay, FKI is 90. We want FKP. Yeah, I'm gonna delete point L, and this circle I can hide. Sec, be right back. All right. But yeah, that was an interesting observation. So GNE is equal to FENQ. Which is FEDQ, right? And here's where we might actually use that these concur. So we want to show FEDQ. Let's see, FEDQ. Yeah, that was it, the 74.93. So we want to show FEDQ is equal to GNE. Or is equal, sorry, is equal to PNQ. And PNQ, maybe it's worth drawing this point here. I wonder. Yeah, it almost looks like these concur, doesn't it? Yeah, that's interesting. Because if that's true, then PNQ is equal to PNL. PNL is anything special about point L? Like apparently A, O, and L are collinear. I'm not sure why, but so what was the 9-point circle of BIC? I think we said something was the 9-point circle of BIC, right?
GDFE.
GDFE. That's an interesting fact. Let's try something. So we have P N. These circles here. Are these tangent at F? Let's see. I don't think so, but it's worth no. Yeah, we still don't know a lot about P. We have to use that P lies on AFE. So yeah, let's see. POL. Maybe we could show POL is 74 degrees. So FENL is 180 minus FEOL. Yeah, this is pretty interesting. So I added in point O. Yeah, what does that mean if those two angles are equal? FENL and POL. For FENL and PFEL. That means that we have similar triangles. Okay, so I wonder if this is a right angle. Is LFEN a right angle? No. All right, 5 more minutes and then I'm going to stop. But I could write out a few things that we noticed. So consider an inversion about the circle with diameter BC. And then we noticed IDQ inverts to itself. So we have GD times GQ equals GB squared. And that means that IDQ inverts to itself. And then we also noticed that the circle GD FE is the 9-point circle of BIC. We want to show that angle PNF equals angle GME. So the inverse of FE lies on I'll say the inverse n lies on line EF. We want to show PNF equals GNE. I think that's everything that we saw. All right, I think I'm gonna stop here. So yeah, if you guys find the solution to this, yeah, post it on Discord because it looks really fascinating. So yeah, we solved a couple of easier problems this session, but then there were a couple of really hard ones, like that one with isogonal conjugates from Mexico, and then this one, which I'm surprised we got as far as we did, but it's thanks to all the participants on the session who have stuck with geometry for a really long time. So for those of you watching on YouTube, thanks for watching. If you'd like to join us in future sessions, feel free to email me at mgreenb801@gmail.com. It's going to be in the description of this video, and we meet every Sunday at 8 a.m. US Central Time. So thanks again for watching and have a great day.